So good evening everyone. Let us continue our discussion on retrofitting and rehabilitation. So this week, that is fourth week lecture, basically will be focusing on fiber reinforced polymer composites, and we'll be basically understanding its various characteristics and also some of mechanics associated with it to understand the load carrying capacity of the fibers and the matrix for the whole composites. So we will firstly go through the introduction, then we will see some derivations, and then we will try to understand even better through some solve examples and also problems. So let us start today's discussion. So the first lecture will be on introduction to composites, types and characteristics. In this lecture, we will cover basically the introduction to composite, types and phases of composite, fiber reinforced polymer composite, types of fibers and their characteristics, types of resins and their characteristics. So what is a composite? The first question in this fiber reinforced polymer structure. So basically composite is formed by the combination of two or more materials on a macroscopic level. One is the reinforcement part and the other is the matrix part. So this reinforcement is basically the fiber and the matrix is the other part. So they are chemically different and separated by a distinct interface, not homogeneous properties. Properties depend upon the position, orientation, geometry, and the amount of fibers and the properties of matrix. The superior properties are compared, they have superior properties as compared to the individual components. So as a group, they showcase superior properties when compared to the individual components. So, three broad classifications of composite materials are there based on the shape of the constituent fibers. They are fibrous composite, particulate composite, and laminated composite. So, fibrous composite basically consists of fibers of one material in a matrix of another. For example, fiberglass embedded in a polymer. The second is the particulate composite, where they are composed of macro-sized particles of one material in a matrix of another. The particles may be of various shapes and sizes and dispersed randomly within the matrix. One example is the cement concrete. So it is an example of particulate composite. And then there is laminated composite, where they are composed of layers of different materials. The examples are plywood having alternate layers of wood veneer. Okay, so these are the types of various composites. So first let us go through the fibrous composite. So inside fibrous composites, there are various types. There are polymer matrix composite, metal matrix composite, ceramic matrix composite, and carbon-carbon composite. So polymer matrix composite is basically polymeric resins as matrix reinforced with fibers of glass, carbon, etc. Metal matrix composite are metals or alloys as matrix reinforced with metal fibers like boron, alumina, etc. Ceramic matrix composite are they are basically ceramics as matrix reinforced with ceramic fibers like silicon carbide, silicon nitride, etc. And carbon-carbon composite, they are basically graphite carbon as matrix reinforced with graphite fibers. So these are the various composite materials. So if we go through the various matrices and the fibers involved and the names of the matrix. Okay, so these are the this is a chart basically. So in polymer, if we say talk about polymer matrices, it can be epoxy, polyimide, polyester thermoplastics, and polysulfone. And the fibers can be E-glass, S-glass, carbon graphite, aramid, Kevlar, and boron. For metal matrix, it can be aluminum, magnesium, titanium, copper, and the fibers can be boron, borsil, carbon graphite, silicon carbide, and alumina. For ceramic, the matrices can be silicon carbide, alumina, glass ceramic, silicon nitride. For fiber, it can be silicon carbide, alumina, silicon nitride, and carbon, both can be fiber as well as matrix. So the composite has different phases, that is fiber phase, matrix phase, fillers, coupling agents, and coatings. So these are the various phases inside a composite. The fiber phase, let us go through each of the types phases. So the fiber phase, it is main load carrying components in composites. It provides the strength and stiffness of composites. They are stronger than the same material in bulk form. They are long and thin. Length is many times greater than its diameter. The diameter is about 1 to 10 microns. Aspect ratio generally ranges from 10 to 100, and fibers can be glass, aramids, carbon, etc. So that is fiber phase. Matrix phase, so it basically supports, protects and transfers the load to the fibers. They are having lower strength, stiffness and density as compared to fibers. It protects fibers from abrasion and forms a protective barrier between the fibers and the environment. And the examples are resins, rubber, cement, sand, mortar, etc. So that is the matrix. Then fillers, so they are used to reduce cost and to achieve a better dimensional stability other than improving the mechanical properties. Examples are carbon black particles, glass microspheres, etc. Then the coupling agent, so that is chemical, they are chemical compounds added to improve the adhesion or bonding between two dissimilar phases in a composite material. They are chemically bond and they chemically bond the dissimilar materials together even in challenging environments. Coupling agents increase the time that it takes for dissimilar materials to fail in service, and the examples are aminosilane, methyacryl silane, epoxysilane, etc. Then coatings. These are basically coupling agents and coatings applied to the fibers. And so basically both coupling agents and coatings are applied to the fibers, and they improve their wettings with the matrix and also to facilitate bond across the fiber matrix interface. So they are mainly for wetting the matrix and proper enhancing the bonding between the fiber matrix interfaces. So, bond mechanism between fibers and matrix. So, there are two types of bond mechanism involved. One is adhesion mechanism and second is friction mechanism. So, adhesion mechanism is basically bond that may be due to absorption, diffusion, chemical bonding or electrical attraction. Whereas frictional mechanism is when the matrix, that is resin example, shrinks onto the fiber. The shrinkage stresses along with the frictional stresses provide the frictional resistance. So through this mechanism, it basically provides bond through the friction mechanism. So they consist of thousands of individual micrometer diameter continuous fibers at a high volume percentage, which is about 20 to 80% to reinforce the polymer resin. The fibers can be of glass fiber, carbon fiber, aramid fiber, basalt fiber, boron fiber, ceramic fiber, jute fiber, and coir fiber. Whereas polymer resins, they can be of polyester resin, epoxy resin, vinyl ester resin, phenolic resin, polyurethane resin, etc. So let us go through some of those fibers. So one is glass fiber. So it is highly elastic modulus. It has high elastic modulus with high strain, and the main ingredient is silica, that is SiO2. So they are chemically inert, excellent. That's why they provide excellent insulating properties. And the various types of glass fibers are E glass, S glass, A glass, C glass, etc. So the different types of glass fibers and their characteristics are as follows. So basically these names have some meaning. Okay, E, S, A, C. So let us see what it means. So if it is E glass, E stands for electrical, and that means it has lower electrical conductivity. If it is S glass, that S strength for S means strength. Okay, so it basically it basically designates high strength. In case of C glass, that C denotes chemical, so that is high chemical durability. M signifies modulus, that is high stiffness. A signifies alkali, that is high alkali or soda lime glass. And D is dielectric, that is having a low dielectric constant. So these are some of the meanings of the letters in the like prefix to the glass. Okay. Next comes the carbon fiber. So they are high elastic modulus. They have high elastic modulus and are resistant to high temperature. The main ingredient here is hydrocarbon. They are chemically inert and lightweight. And the various types of carbon fibers, like they provide standard high strength, high modulus, and ultra high modulus. So these are some of the specialty of carbon fiber. Next comes the aramid fiber. So they provide high elastic modulus, resistance to damage, fatigue and stress rupture. So these are hydrocarbon aromatic polyamide molecular chains. They have high moisture absorption, low melting temperature and lightweight. and the types can be like Kevlar 29, Kevlar 49, and Kevlar 149. So these are some of the types of aramid fibers. Next comes the boron fiber. So they have very high tensile modulus, and they are lightweight and have a relatively large diameter. The main ingredient is boron. They are capable of withstanding comparatively large compressive stresses and provide excellent resistance to buckling. So that is some of the characteristics, okay, of boron fiber. Next comes the ceramic fiber. So they have high elastic modulus, they have high strength, high temperature capabilities, and free from environmental attack. The examples are silicon carbide (SiC) and aluminum oxide Al2O3. So these are the examples of ceramic fibers. Then there are basalt fibers. So they have high tensile strength, high modulus of elasticity, and the main ingredients are silica, alumina, and iron oxide. So they provide better temperature resistance, they provide impact resistance and chemical stability. They are useful for long-term application in high pressure, chemical, and thermal stress environments. Next comes polymer. So polymer consists of very large molecules that are made up of small molecular units or mers linked together into chain-like or network structures. So poly means many and mers means the smallest molecular unit. Okay, so many small molecular units, when they are merged and they are connected, so it becomes polymer. So if the polymer is formed by process, it is called thermoplastic. Examples of polymer which is made by process are thermoplastic and thermoset. Examples of polymers made by type, okay, if we differentiate by type, it can be plastic, rubber, adhesive, resin, and there are also natural polymers like cellulose, lignin, which is found in wood. So if we talk about thermoplastics, they basically soften and liquefy on heating and can be reshaped many times, and they are used over a wide range of temperature from 100 degrees centigrade to 300 degrees centigrade. The advantages are improved fracture toughness over the thermoset matrix, and they have chemical inertness and pleasing appearance, and they are lower in cost in the manufacturing of finished composites, and they are basically widely used in several industries. So that's why thermoplastic are very significant nowadays. However, it also has some disadvantages, like it is used only at ambient temperature. A significant problem encountered also while mixing fibrous material with a thermoplastic matrix due to its high viscosity at normal temperature, and they also exhibit considerable strain at relatively lower stresses. The examples of which can be polyethylene, polyvinyl chloride, and polypropylene, polystyrene, etc. Okay. Next, let us talk about thermosets. So they solidify by a chemical reaction, and they cannot be recycled or reshaped by heating. They are widely used as a matrix material for fiber reinforced composites in structural composite components. The advantages are basically they improve thermal stability and chemical resistance, and the disadvantages are they have limited storage life at low temperature. The low value of strains to failure, it has low value of strains to failure, and it requires more time in fabrication. And the examples are phenolic resin, epoxy, unsaturated polyester, and polyurethane. So if we talk about polymer by type, so it can be plastic. Okay, so these two were polymers by processes. Okay, so if we talk about polymer by type, so first is plastic. So they are materials that can be molded into any shape. Second is rubber, which is basically a material with large elastic deformation, and they are basically natural as well as synthetic. Okay, and adhesives are materials that is used to join materials or glue, and resins is it can be used as resin plus hardener, that is material that is used in fiber reinforced composites, thermoset polymer, etc. So the types of thermosets can be polyester resin, epoxy resin, vinyl ester resin, phenolic resin, and high performance resin. And the polyester resin, basically it is the most commonly used resin in glass reinforced plastic construction. They are unsaturated polyester resin formed by the reaction of a saturated difunctional acid or aromatic acid, then an unsaturated difunctional acid which is aliphatic, and a difunctional glycol which is aromatic or aliphatic. Okay, so it can be both, and they have reasonable cost and ease of application, so that is also a benefit. Then let us talk about epoxy resin. So they are superior to polyester resin in terms of mechanical properties. They provide resistance to degradation by water and other solvents. It gives better adhesion to reinforcing fibers. The advantages of epoxy resins in industry can be, firstly, the ease with which it can be processed. Secondly, the excellent mechanical properties in composites. And thirdly, high hot and wet strength properties. So these are some of the characteristics. Now next let us talk about vinyl ester resin. So they are superior to polyester resin because it offers greater resistance to water. It provides superior chemical resistance and superior retention properties of strength and stiffness at elevated temperatures. They are construction and marine industries. Okay, so they are basically widely used there in both construction, small high performance hulls such as racing canoes and speedboats. Okay, so these are some of the uses. Now let us talk about phenolic resins. So they provide excellent fire resistance properties, and they're used in high temperature application areas. They have inferior mechanical properties to both polyester resin and epoxy resin, but higher maximum operating temperature. They have cold cure varieties of phenolic resins used for contact molding of structural laminates, and the phenolic resins only matrix used in aircraft interior and other locations of public occupancy and ship industry. So these are some of the uses. Then let us talk about the high performance resins. So their attempts are on for the development of matrices with better properties at elevated temperatures. Generally, the processing characteristics deteriorate with the increase of thermal stability. Most highly developed systems can be bismaleimide, that is BMI, and polyamide, PI. So basically, in this lecture, we basically understood the basically what is composite, that is its introduction, the types and phases of composite, fiber reinforced polymer composite, types of fibers and their characteristics, and types of resins and their characteristics. So in the next lecture, we will be basically studying about the properties of fibers, resins, and FRP composite. So it will cover the properties of fibers and resins, stress-strain relationships, the properties of FRPC, stress-strain relationships, advantages and limitations of FRPC, and applications of FRPC. So let us start this. So as we studied, so there were different types of fibers. Okay, so it can be glass, carbon, aramid, boron, ceramic, and basalt. So if we see here, it shows the stress strain relationships of different types of fibers. Okay, so this high strength carbon, so it is very high. This is high strength carbon. This is high modulus carbon. This is Kevlar. This is S glass. This is E glass. So this has a very high elastic modulus. That's why it is high modulus carbon. So if we study like the various properties associated with the different types of fibers, standard fibers have been shown here, ranging from typical diameter, specific gravity, tensile modulus, tensile strength, ultimate elongation, and coefficient of thermal expansion, which is alpha. So if we talk about the different types of resins, so there can be polyester, vinyl ester, epoxy, phenolic. So here also the stress versus strain graph has been shown between those at various temperatures. Okay. So the approximate properties of the different types of thermostatic resins basically, which are polyester, vinyl ester, epoxy, phenolic. So they are also shown in terms of gravity, specific gravity, tensile modulus, Poisson's ratio, tensile strength, compressive strength, elongation, coefficient of thermal expansion, and water absorption. So basically by going through this, we can basically have an idea of what are the various properties of FRPC. So the fiber properties dictate the stiffness of unidirectional composites. The property is strongly dependent on the direction of fiber. So it is so basically they are different along and across the direction of fibers. So therefore it is very strongly dependent. Properties like tensile strength, tensile modulus is in a unidirectional FRP, at a maximum value along the direction of fibers and minimum at its perpendicular direction, which is obvious. And the properties can be tailored or manipulated or amended to meet the design requirements. That's why it has various utility. So if we see about the general stress strain relationships of fiber, matrix and composite, it is like this. So the fiber has the maximum modulus, okay, and the matrix has the least, and combining we get the composite. So it is in between. So the stress strain relationships of typical fiber reinforced polymer composites are shown here for various types of material. So these are the stress strain curves of typical unidirectional composites in the fiber direction. So now let us study lamina and laminates. So a single ply or lamina is formed by a combination of a large number of fibers in a thin layer of matrix. Fibers may be continuous or discontinuous, arranged in a specific direction or in a random orientation. Unidirectional ply or lamina, so two-dimensional sheet with very small thickness and all the fibers are aligned in one direction. The thickness of lamina ranging from 0.1 to 1.0 mm, and the examples can be FRP rebar, FRP sheet and FRP fabric. So this is the unidirectional lamina. A number of unidirectional plies, when stacked at various on-axis or off-axis angles relative to the global axis, form a multidirectional laminate. The stacking sequence is used to define the layup, and they can be unidirectional laminate as well as multidirectional laminate. So let us go through each of them. So unidirectional laminate, in this case, all the fibers are aligned parallel to one axis. Okay, so that is say x-axis. So if you can see, this is the x-axis. Strength is much stronger in that axis, that is the x-axis, is compared to the strengths in other axis. So that's why it is unidirectional. So if the layers, so fibers are in one axis, and because it is stacked in a particular direction, so it is unidirectional. So next, let us study the multidirectional laminate. So here, formed by cementing plies with different fiber orientations. So as you can see, one orientation is like this, one is like this, one is like this, one is again like this, like this. So there are three types, okay, three types of orientations, okay. So that's why it is shown here 0, 2, 92, 45, minus 45, 3. So these are numbers, okay, designating the various positions. So formed by cementing plies with different fiber orientations defined by the stacking sequence of the ply groups, and examples are plywood with veneers oriented in different directions. So this is the composite and these are the multidirectional laminates. So the properties can be predicted from the uh, properties of fiber in matrix, obviously, because it is a composite made of both. So if we combine both, the properties can be predicted. And here this study is basically called the micromechanics, okay. So that is fiber level analysis to relate mass or weight fraction of the constituents to their volume fractions, to estimate stiffness properties of composites, to approximate the longitudinal strength and longitudinal modulus of fiber sheet material by ignoring the mechanical contribution of matrix, okay. So that is basically the uses, okay. So in that regard, we have to first understand three types parameters of elastic property, okay. So one is orthotropic, one is transversely isotropic, and one is isotropic, completely isotropic. So when we talk about orthotropic, that means that properties are different along three mutually orthogonal directions. So orthogonal is 90-degree, okay. So when properties are different along three mutually orthogonal directions, it is orthotropic. Transversely isotropic means properties are same in two mutually orthogonal directions. So that is, transverse is basically the section, okay. So along the section in one plane, when the properties are same, okay, so that is x-axis and y-axis, then we can say that it is transversely isotropic. And when the properties are same in all the three mutually orthogonal directions, then it is called isotropic. So when it is completely all are different, it is orthotropic. When it is two along the section it is same but along the axis it is different, it is transversely isotropic. And when all the directions have same properties, it is completely isotropic or simply isotropic. So orthotropic material, it has three mutually perpendicular planes of material symmetry. The planes normal to x and y and z axis are planes of symmetry. Planes axis x, y, z are principal directions. Properties different in x, y, and z planes. 9 independent elastic constants Exx, Eyy, Ez, mu xy, mu yz, mu zx, gxy, gyz, and gzx. Okay. So these are composite material with fibers oriented differently along x, y, and z axis. So next is the transversely isotropic material. So properties are same in two mutually orthogonal directions, that is y and z plane, and different in x plane. So here we have they have substituted x with y and y with z and z with x. Okay, and then planes y and z are isotropic. So five independent elastic constants Exx, Eyy, mu xy, mu yz, and gxy. So these are the elastic modulus, mu is the Poisson's ratio, and g is the shear modulus. Okay, and composite material with fibers oriented similarly along y and z planes and differently along x plane. Then there is isotropic material. So here properties are same in all three mutually orthogonal directions, that is x, y, and z. The two independent elastic constants here are E and mu. Okay, so they don't have any this one subscript. Okay, so that's why, because all the directions, in all directions the properties are same. Okay, so two independent elastic constants, elastic modulus, and your Poisson's ratio, and the examples are metals. So this is the example of an orthotropic material. Okay, so all the in all the axes it is different, the basically the properties, and this is the example of transversely isotropic material. So here along the section it is the same. Okay, so that's why it is represented by dot dot, whereas here the lines have different widths. Okay, so that is the difference. Okay, so because it has different properties, and this is the same along the section. The typical values of elastic constants of different composites fibers along x-axis have been shown here for materials graphite plus epoxy, glass plus epoxy, and Kevlar plus epoxy. So if you see here, epoxy is the matrix and graphite, glass, and Kevlar are the fibers. Okay, and these are present along the x-axis. So these are the properties of different composites. So what are the advantages of fiber reinforced polymer composite? So basically they are non-metallic and therefore resistant against corrosion, because the electrochemical or electrolysis reaction does not occur here. They are lightweight, they have high strength to weight ratio, they have high ultimate strength and Young's modulus. They have high fatigue resistance. They have low thermal conductivity. They are bad conductor of electricity and non-magnetic. They are available in rolls, so easily transported. They have easy fabrication, erection, thereby economical for use at site, and they have less maintenance. So these are the properties of fiber reinforced polymer composite. The limitations of FRPC basically are they have erratic plastic behavior and less ductility. The resins are being organic in nature and they are susceptible to burn. The loss of strength, they are susceptible to loss of strength at high temperature. They are susceptible to local unevenness, and they are difficult to use in small quantity, and also they are comparatively expensive. So these are the issues or drawbacks of using fiber reinforced polymer concrete composite. The applications of FRPC can be in various industries like marine industry, aircraft and space field industry, automobile industry, sports goods industry, and civil infrastructure. So in marine industry, they are used in lifeboats, small and large boats, radar dome, mast, boat hulls, hovercraft, submarine, naval vessels, etc. So there it is used. For aircraft and space field basically, so they are used in aircraft components, uh, helicopter blades, missiles structure missile structures, spacecraft structures, satellite structures, etc. In automobile industry, they are used in car exterior parts like hood or door panels, components of racing cars, parts of engine, and in sports goods like tennis rackets, snow skis, snow skies, fishing rods, archery bows, javelins, golf items, surfboards, etc. And in civil infrastructure, which is for our importance, they are used for retrofitting of existing structures. Okay. So in this lecture, we basically understood the properties of fibers and resins, stress-strain relationships, properties of FRPC, stress-strain relationships, advantages and limitations of FRPC, and applications of FRPC. So the next lecture will be basically understanding the micromechanics involved associated with composites. And it will cover basically the micromechanics of composites and determination of elastic moduli of composites. So let us start the next lecture. So the properties of composite depends upon the relative proportions of the fibers and the matrix. The relative proportions in terms of weight fractions or volume fractions, analysis of estimation of load sharing by fibers and matrix based on their properties and the micromechanical aspects of their volume weighted relationships. So before starting, we have to take some basic assumptions or considerations. So they are basically: one, both fiber and matrix are homogeneous and isotropic. Two, fiber, matrix, and the resulting composite exhibit linear elastic behavior. So basically, it is recoverable. Okay, so it is temporary. That's why linear elastic. Uh, so deformation is temporary. So then fibers are in uniform, regularly spaced and perfectly aligned. Matrix is free of voids. Perfect bond exists between fibers and matrices, so that no slippage occurs at the interface, and lamina is in a stress-free state, that is, no residual stress is present. And these are some of the terminologies involved for the calculation and derivations. So volume and weight fractions. So capital VC is volume of composite, capital WC is weight of composite, rho C is density of composite, capital VF is volume of fiber, capital WF is weight of fiber, rho F is density of fiber, capital VM is volume of matrix, capital WM is weight of matrix, rho M is density of matrix. So if we see here, the idealization of unidirectional composites, so there are two phases: fiber phase and matrix phase. So fiber phase is having a weight of F, WF, volume of VF and area of AF, and similar is the case with matrix phase, okay, with the subscripts M, okay. So here will be basically we are seeing the fiber volume fraction, matrix volume fraction, matrix weight fraction, and fiber weight fraction. So we'll see that. So the volume of composite VC, capital VC, if it is void free, it will be equal to VF plus VM, that is volume of fiber and volume of matrix. Now volume fraction of fiber and volume fraction of matrix can be defined as small v. Okay, so whenever a small v comes, it means volume fraction. Okay, so volume fraction of fiber therefore will be capital VF by VC. Similarly, volume fraction of matrix will be capital VM by capital VC. So this small vf plus small vm, that will be again equal to capital VC by capital VC, right, according to this, and that is nothing but 1. And weight fraction of fiber and weight fraction of matrix similarly will be small wf equal to capital WF by capital WC, and small wm is capital WM by capital WC, and if we add both the terms, again it will be equal to 1. So this capital WC is equal to capital WF plus capital WM, and therefore this can be written as rho into V, right? Density into volume is weight. So this implies rho C into VC is equal to rho F into VF plus rho M into VM. So if we divide both sides by VC, we get rho C equal to rho F into small vf plus rho M into small vm. And similarly, replacing volumes in terms of weights, okay, and densities in equation 1. So this equation, so if we replace volume with weight and density, we get capital WC by rho C equal to capital WF by rho F plus capital WM by rho M. So again, dividing both sides by WC, we get 1 capital WC, we get 1 by rho C equal to small wf by rho F plus small wm by rho M. Okay, so this is the derived equation. Now if we see here, the vf by wf, okay, small vf by small wf, so we got the values here. So small vf is your capital VF by VC, and small wf is capital WF by capital WC. So if we see here, so this is equal to W capital VF by capital WF into capital WC by capital VC, right? And this is equal to rho C by rho F, okay? Because kg, this is where density is weight by volume, right? So it will be capital WF by capital VF, that is rho F, and WC by rho VC is rho C. So VF by WF equal to rho C by rho F. So that means that small VF is equal to small WF into rho C by rho F, okay? And in a similar way, we can prove that small Vm equal to small Wm into rho C by rho M, okay? So these are the equations. Now here, let us see some important terms. So this ECL is equal to Young's modulus of composite in the direction of fiber, that is longitudinal. Similarly, sigma CL is composite strength in the longitudinal direction. Epsilon CL is strain in composite in the longitudinal direction. ACL is cross-sectional area of the composite particular to the longitudinal direction of fiber. And then ECL is equal to Young's modulus, ECT is equal to Young's modulus of composite in the transverse direction, that is perpendicular to the longitudinal modulus. Similarly, sigma CT is compressive strength in transverse direction, epsilon CT is strain in composite in transverse direction, and ACT is cross-sectional area of the composite parallel to the direction of the fiber. Similarly, EF will be Young's modulus of fiber in the direction of applied load. Sigma F is equal to fiber strength in the direction of applied load. Epsilon F is strain in fiber in the direction of applied load. Capital AF is cross-sectional area of the fiber perpendicular to the direction of applied load. Capital EM is Young's modulus of matrix in the direction of applied load. Sigma M is matrix strength in the direction of applied load. Epsilon M is strain in matrix in the direction of applied load. And capital AM is cross-sectional area of the matrix perpendicular to the direction of applied load. So now let us see how it is used. Okay, so this PC is basically the load. Okay, load in the acting on the composite. Okay, so unidirectional composite member longitudinally stressed. Okay, so this was basically the original. This was the solid line is the original shape when it is stressed longitudinally by some tensile load. So this is the deformed section. Okay, so here the assumptions: the rod extends uniformly with no delamination between the matrix and fiber. So delamination was like removal of layers from the top. Okay, so that was, if you remember, it is delamination from the surface. And when the depth was high, it was also called as spalling, if you remember in the initial classes we discussed. So the rod extends uniformly with no delamination between the matrix and fiber, and the transverse sections that were plane before bending remains plane also after bending. Okay, so this is also an assumption. This means strain in the matrix and strain in the fiber are the same basically. Okay, so that's why the plane, this is also used in the simple beam theory also, these assumptions. So plane before bending remains plane also after bending, so that strain in matrix and strain in fiber are the same. So using this philosophy, we can say that epsilon CL equal to epsilon F is equal to epsilon M. Okay, so that is basically equal to delta L by capital L. Okay, so therefore EF equal to sigma F by epsilon F, and sigma F equal to EF into epsilon F, whereas EM equal to sigma M by epsilon M, that is sigma M equal to EM into epsilon M. So load taken by the composite PC is basically load taken by the composite is the load taken by the fiber and matrix, that is PC equal to PF plus PM, or we can say sigma CL into ACL equal to sigma F into AF plus sigma M into AM is equal to EF into epsilon F into AF plus EM into epsilon M into AM, which is equal to EF into AF plus EM into AM into epsilon CL. Okay, so because epsilon F equal to epsilon M equal to epsilon CL. Okay, therefore sigma CL into ACL equal to EF into AF plus EM into AM into epsilon CL, or sigma CL by epsilon CL equal to ECL, okay, which is equal to EF into AF by ACL plus EM into AM by ACL. Okay, or ECL equal to EF into AF into L by ACL into L plus EM into AM into L by ACL into L, just multiplying and dividing by L. Okay, or a ECL equal to EF into VF by VCL plus EM into VM by VCL. Okay, or ECL equal to EF into VF plus EM into VM. Okay, so they have converted into volume fraction. Okay, so that is a relation. And similarly, based on equation 20, okay, it can be also written as sigma CL equal to sigma F into so basically sigma CL equal to sigma F into yeah, because this EF is equal to sigma F by epsilon F, and EM equal to sigma M by epsilon M. Epsilon CL, epsilon F, and epsilon M is equal, so all get cancelled. Okay, so therefore sigma CL equal to sigma F into AF by ACL plus sigma M into AM by ACL, which is equal to sigma F into VF plus sigma M into VM. So that is, we have converted this into your volume fraction. Okay, because again if we multiply into L, so it will be VF by VCL, that is VF, and this is capital VM by capital VCL, that is VM. So using this, so from this 23 we get that ECL equal to EF into VF plus EM into VM. Okay, and the sigma CL equal to sigma F into VF and plus sigma M into VM. Okay, so equations 25 and 26, they are known as a rule of mixtures. Okay, so basically to get the longitudinal this one composite elastic modulus, you have to multiply, you have to just add the product of elastic modulus and volume fraction of fibers and this matrix. And similarly for getting the longitudinal stress in composite, so you have to just measure the you have to just uh, add the product of the stress and volume fraction of fibers and matrices basically. Okay, so so that is basically you will get the strength. Okay, so now the fraction of the load carried by fibers in a unidirectional lamina, so that is basically PF by PC, which is equal to sigma F into VF by sigma F into VF plus sigma M into 1 minus VF, and that is equal to EF VF by EF VF plus EM into 1 minus VF. Okay, so using those relations we find this, and this from 25 basically. So yeah, so this 1 minus VF, I think you have understood, because we are considering that there is no void. Okay, so therefore if this is 1, so if this is VF, so the VM will be equal to 1 minus VF, because VF plus VM equal to 1, because this is the void fraction. Okay, so adding both will be 1. Okay, so equation 25 can be also written as ECL equal to EF minus EM, okay, into VF plus EM. Okay, so that can also be written for equation yeah, 25. Okay, so just substituting the values basically. Okay, so the variation of load carried by the fiber with fiber volume fraction for varying modular ratio is also shown here. Okay, so that is basically for longitudinal modulus. Now let us come for the transverse modulus of composite. So this is composite under transverse stress. So that is basically the load is acting in the perpendicular direction, okay, or along the transverse section. Okay, so if you see here, along the basically the load is acting along a plane or a section which is parallel to the axis of the fiber. Okay, the longitudinal axis, so that is the transverse. Okay, so here so if you see here, this is the TF, so this is the thickness of the fiber, and TM is the thickness of the matrix. Okay, and this is a deformed section. So here also we assume that no separation between fiber and matrix, and each layer has the same area on which the load acts. This means each layer experiences the same load and the same stress. Okay, so sigma ct equal to sigma f equal to sigma m, okay, as we studied. So therefore total transverse displacement is delta tc. Okay, so delta tc is the total transverse displacement, and that is equal to delta tf plus delta tm. So also BLTF equal to VF and BLTM equal to VM, which is self-explanatory, and BLDC equal to VC. So therefore, total transverse displacement is delta TC equal to delta TF plus delta TM. Now epsilon CT is delta TC by TC equal to delta TF by TC plus delta TM by TC, and therefore EC epsilon CT is delta TF into TF by TF into TC plus delta TM into TM by TM into TC. So we have multiplied TF and TM, both numerator and denominator. So epsilon CT becomes epsilon F into TF into LB by TC into LB, and plus your this epsilon M into TM into LB by TC into LB. Okay, and basically, so this delta TM by TM is epsilon M and delta TF by TF is epsilon F. Okay, so therefore epsilon CT is equal to epsilon F into VF plus epsilon M into VM. Okay, replacing strain terms by their corresponding modulus and stresses yields sigma CT by ECT equal to sigma F by EF into VF plus sigma M by EM into VM. And from equation 37, the relation therefore becomes 1 by ECT equal to VF by EF plus VM by EM. Okay, so it is like the series parallel thing in your electrical circuits, right? Resistance equation, if you remember. So it is similar, something like that. So now here we have to take the reciprocal in the transverse direction. Okay, or 1 by ECT equal to VF by EF plus 1 minus VF by EM. So this is also important relation. So here it is shown the variation of ECT, that is the elastic modulus of the composite along the transverse direction with the fiber content. So if you see here, when the fiber content is increased, okay, the elastic modulus also increases exponentially, okay, along the transverse section. Similar is the case with also the this one, the longitudinal section. So it increases with the fiber, okay, because mostly the fiber takes the load, okay, it provides the strength basically. So so that is about the transverse modulus of composite. Now let us see the in-plane shear modulus. The composite element is subjected to uniform shearing, that is sliding, and complementary shearing stresses along the boundaries. So this is tau c, tau c. This is the matrix. This is the fiber. Okay, so this is the overall deformation, and this is the in-plane shear stress acting. So this is a composite under in-plane shear stress. The shearing stresses in the fiber and matrix are equal. Thus, tau c equal to tau f equal to tau m. Okay. So total shear deformation of composite delta c is equal to delta f plus delta m. Delta c equal to mu c tc, delta f equal to mu f tf, delta m equal to mu m tm. Therefore, gamma c tc equal to gamma f tf plus gamma m tm. Okay. So the gamma c tc equal to gamma f tf plus gamma m tm, or gamma c equal to gamma f into tf by tc plus gamma m into tm by tc, which becomes gamma c equal to gamma f into tf bl by tc bl, just multiplying and dividing bl, plus gamma m into tm bl by tc bl. Or shear strain of the composite, gamma c equal to gamma f vf plus gamma m vm, or tau c by gc equal to tau f by gf vf plus tau m by gm vm, or so 1 by gc equal to vf by gf plus vm by gm. So this formula is also similar to the elastic modulus of transverse section. So that is for in-plane shear modulus. And here you can see the variation of gc. That is the in-plane shear modulus, okay, along the this one for the composite, okay, with the increase in the fiber volume fraction, okay, so it also increases exponentially. Then for in-plane, then let us talk about the Poisson's ratio. For in-plane loading of a composite, nu CL is equal to measure Poisson's ratio, which relates longitudinal strain and transverse strain. So that is basically your longitudinal strain divided by transverse strain, and nu CT equal to minor Poisson's ratio, okay, which relates transverse strain and longitudinal strain. So it is the opposite. Okay, so your this one, the measure Poisson's ratio nu CL, so that is basically transverse strain by longitudinal strain. So we know Poisson's ratio is equal to lateral strain by longitudinal strain, right? So that is basically this epsilon d by epsilon I L. So Poisson's ratio is basically the measure Poisson's ratio. Okay, and the transverse strain in fiber and in matrix are epsilon tf equal to minus nu f epsilon L, and epsilon tm is equal to minus nu m into epsilon L. Also epsilon tf equal to delta f by tf, epsilon tm equal to delta m by tm, and epsilon t equal to delta c by tc. Now delta c equal to delta f plus delta m, and or epsilon t into tc equal to epsilon tf into tf plus epsilon tm into tm. Okay, so substituting minus tc vcl nu cl epsilon L equal to minus tf nu f epsilon L minus tm nu m epsilon L, or epsilon cl is equal to nu f into tf by tc plus nu m into tm by tc, or nu cl equal to nu f vf plus nu m vm. Okay, so the measure Poisson's ratio also follows the rule of mixtures. Okay, so that is the basically we it is like a series connection of electrical circuit. Okay, so it is a rule of mixture, and minor Poisson's ratio is the other way, so it is nu cl by ecl equal to nu ct by ect. Okay, so this is the variation of Poisson's ratio of the composite with the fiber content. So as it increases, the fiber content increases, the Poisson's ratio of the composite also increases. And at a fiber content of 1, so the composite also has a Poisson's ratio same, because everything is fiber. Okay, and similarly if everything is your matrix, because fiber content will be 0, so volume fraction completely will be 1. Okay, for fiber this volume fraction of matrix, when the volume fraction of fiber will is 0. Okay, so then vc also takes the value of vm. Okay, so that is the this one that is the value. So this is the Poisson's ratio. Okay, so this is the matrix Poisson ratio equal to composite Poisson's ratio when the fiber content volume fraction is 0. Okay, because the whole composite is made up of the matrix. Okay, so we can say that we in this lecture we learned the macro mechanics of composites, and also we understood the determination of elastic moduli of the composites. Now we will be in the next lecture also we will be continuing about the micromechanics of composites. Okay, so here we will be basically try to understand it in more detail through solving of a few numerical problems. Okay, on micromechanics of composites. So the first question or the first problem is an e-glass e-glass vinylister unidirectional rod. Okay, so here e-glass is the fiber and vinylister is the matrix. Okay, so an e-glass vinylister unidirectional rod is to be used as an FRP reinforcing bar. The rod has 80% fiber weight fraction. So assuming no voids in the composite, determine the fiber volume fraction and the stiffness properties of the composite. So here are the properties of e-glass fiber. The density rho f is equal to 9.4 into 10 to the power minus 2 pound per inch cube. Elastic modulus EF is equal to 10.5 into 10 to the power 6 psi. Poisson's ratio nu f is equal to 0.20. On the other hand, vinyl ester matrix has a density of 4.57 into 10 to the power minus 2 pound per inch cube. Elastic modulus of EM equal to 0.5 into 10 to the power 6 psi, and Poisson's ratio V Poisson's ratio nu m equal to your 0.38. Okay, so the question asked is determine the fiber volume fraction and the stiffness properties of the composite. Okay, so let us see. So the volume of composite Vc equal to Vf plus Vm. So replacing volumes in terms of weights and densities, we get capital Wc by rho c equal to capital Wf by rho f plus capital Wm by rho m. So dividing both sides by Wc, the density of composite is written as 1 by rho c equal to Wf by rho f plus Wm by rho m. So 1 by rho c equal to 0.8 by 9.4 into 10 to the power minus 2. So these values are given in the question, plus 0.2 by 4.57 into 10 to the power minus 2, so which comes out to be 7.76 into 10 to the power minus 2 pound per inch cube as the composite density. Okay, so therefore the fiber volume fraction basically it will be equal to Wf into rho c by rho f, which becomes equal to the 0.66. And since there is no void and similar using the similar formula, the matrix volume fraction becomes 0.34. The unidirectional composite, when loaded along the direction of the fibers, it is assumed that the strain in the fiber matrix and composite are the same. Considering this, the elastic modulus of composite along the fiber direction is EC equal to EF into VF plus EM into VM. So that is the rule of mixture. Okay. So EC becomes 10.5 into 10 to the power 6 into 0.66 plus 0.5 into 10 to the power 6 into 0.34, which becomes equal to 7.1 into 10 to the power 6 pound per square inch. Thus, elastic modulus of composite along fiber direction EC equal to 7.1 into 10 to the power 6 psi. Okay. The unidirectional composite, when loaded transverse to the direction of fibers, it is assumed that the stress in the fiber matrix and composite are the same. Considering this, the elastic modulus of composite perpendicular to the fiber direction is 1 by ECT equal to nu F by EF plus nu M by EM. So basically, this this value, okay, so that is the basically volumetric strain per unit resistance to transverse deformation. Okay. So 1 by ECT equal to 0.665 10.5 into 10 to the power 6 plus 0.34 by 0.5 into 10 to the power 6. Okay, and the value for ECT, that is elastic modulus of composite perpendicular to the direction of fiber, or transverse elastic modulus, comes out to be 1.35 into 10 to the power 6 pound per square inch. So the measure Poisson's ratio, again using the rule of mixture, it becomes 0.2 into 0.66 plus 0.38 into 0.34, that is nu FVF plus nu MVM, which comes out to be 0.26. And the minor Poisson's ratio, okay, so it is nu C by EC equal to nu CT by ECT relation. Okay, so here Poisson's ratio per unit resistance to deformation is constant for the same material. That's why we can relate it. Okay, so using the values, we get the nu CT value as 0.049. Okay, now let us see the shear modulus of the composite. So that is again calculated using this equation, 1 by GC equal to VF by GF plus VM by GM. That is, we are basically calculating the volumetric strain per unit resistance to shear deformation. So if we remember, the consideration was that both fibers and matrix are homogeneous and isotropic. So yeah, like considering that, and basically we, if we consider that basically, so we can calculate the shear modulus of fiber and matrix using these relations. Okay, so basically the if we remember from our physics classes, the shear modulus of any material is equal to G, which is G basically, it is equal to E by 2 into 1 plus nu. Okay, so therefore shear modulus of fiber GF equal to EF by 2 into 1 plus nu F, which comes out to be 4.375 into 10 to the power 6 psi. And similarly GM, which is the shear modulus of matrix, it is equal to EM by 2 into 1 plus nu M, which comes out to be 0.18 into 10 to the power 6 psi. So therefore, the shear modulus of the composite, that is 1 by GC equal to nu F by GF plus VM by GM. Using this equation, we get the shear modulus of the composite, that is GC value as 0.49 into 10 to the power 6 pound per square inch. Okay, so we have found out every parameter. So we got the our this one stiffness properties as well as the fiber volume fraction. Okay, which was 0.66. Next question, that is second problem. A glass fiber reinforced nylon composite contains E-glass fibers of 30% by volume. Calculate the percentage of load carried by the fibers when the composite is loaded. The glass fiber has an elastic modulus EF of 72 gigapascal, and the nylon matrix has an elastic modulus EM value of 2.8 gigapascal. So basically we need to calculate the percentage of load carried by the fibers when the composite is loaded. Okay, so let us see how to solve it. The unidirectional composite, when loaded along the direction of the fibers, it is assumed that the strain in the fiber matrix and composite are the same. So epsilon C equal to epsilon F equal to epsilon M. The strain can be written as epsilon F, which is equal to sigma F by EF, and epsilon M equal to sigma M by EM. Equating the two, we get sigma F by, because all are equal, so sigma F by EF equal to sigma M by EM. or sigma f by sigma m equal to F by Em, which is 72 by 22.8, which is 25.71. Thus, stress in fiber sigma f equal to 25.71 sigma m. So now the volume fraction of fiber Vf is equal to Vf, capital Vf by capital Vc, which equal to AFL by ACL, which is equal to AFL by AFL plus AML, because we are considering void free. So this two combines the composite volume, right? So it is equal to AF by AF plus AM, that is 0.3. So AF equal to 0.3 into AF plus AM, or 0.7 AF equal to 0.3 AM, or AF equal to 0.3 by 0.7 AM, right? So now the question which is asked is we need to calculate the fraction of load to be carried by the fibers. So PF by PC, right? So that is equal to sigma F into AF by sigma F into AF plus sigma M into M. So substituting the sigma F values, okay, and AF values as we derive here and in the previous slide. So basically we get the ratio is 0.9168, or the percentage is 91.68%. So therefore the fibers carry 91.68% of the applied load on the composite. Okay. So in this lecture we basically understood some of the numerical problems and solutions related to the micromechanics of composites. Next lecture we will basically be understanding the manufacturing of the fiber reinforced polymer composites. So here we will be covering the different methods of FRP manufacturing. So the FRP materials can be manufactured in three ways. Basically, one is three broad ways. One is contact molding, one is compression molding, and one is filament winding. Okay. Inside contact molding, there are two types. One is hand layup and one is spray up. Inside compression molding, there are four types. One is match die molding, one is forming method employing gas pressure, one is close mold method employing low pressure, and one is pultrusion. Okay, so we'll be going through each of them in detail. So contact molding, basically it is the simplest, oldest, and most commonly used method for the manufacture of both small and large reinforced products. The open mold method of molding thermosetting resins, polyesters, and epoxies in association with fibers, usually glass fiber mat, fabric, or woven roving. A chemical reaction initiated in the resin by a catalytic agent causes hardening to a finished part. Mold is prepared with a flat surface, a cavity female, and a positive male plug made from wood, metal, plastics, reinforced plastics, or other combinations. So that is your contact molding. So here, wax polishing of the mold using materials like wax, polyvinyl alcohol, PVA, fluorocarbons, silicones, then release papers, films, or uh, films or liquid, depending upon the type of surface to be molded, the degree of luster desired, and painting or the requirement of other secondary finishing. Gel coating of the mold surface using specially formulated resins, normally a polyester mineral fill pigmented layer of thickness 0.3 to 0.5 millimeter for providing smooth external surface. And then there is hand layup method and spray up method. Okay, so these are the various types. So now let us see them also, the types. First is hand layup. The fiberglass is in the form of chopped strand mat, cloth, or woven roving. The pre-measured resin mixed with a catalyst hardener deposited liberally on the gel coated surface of the mold or on a previous ply of impregnated fibers. The resin catalyst mixture deposited on the reinforcement using a spray gun, which automatically meters and combines the ingredients. Adjacent strips of reinforcement within a ply may be lapped or butted, and your this strips of reinforcement forming the subsequent plies must be placed staggered to avoid a line of weakness, and the thickness is controlled by the layers of materials placed against the mold. Okay, so that is hand layup. To ensure complete removal of entrapped air and wet out, roller dispenser or brush or uh, spray gun is used to compact the material against the mold. And the first layer of reinforcement is usually a thin randomly oriented fiber mat designed to reinforce the resin-rich surface of the moldings and improve surface finish. That is a hand layup process. Okay. So then there is spray up, and this is the spray up process. So it is partially automated process. The fiberglass in the form of chopped strand or woven roving. Fiberglass roving fed through a chopper on the spray gun and blown into a resin stream. Fibers sprayed simultaneously with resin mixed with catalyst and accelerator using a spray gun. The glass resin mixture is consolidated by manual rolling to remove air, to compact the fibers, and to smoothen the surface, providing a laminate. So, what are the advantages of this? That is the contact molding. So, which includes both the hand layup and spray up processes. Okay. So, the advantages of contact molding are design flexibility, large and complex items can be produced, minimum equipment investment and low tooling cost. Startup lead time means start working in this method, and initial pre-requirement costs are minimal. Semi-skilled workers can be easily trained. Molded in inserts, metallic thread or other insert through the composite, and structural changes are possible. Sandwich constructions possible. Okay. So these are advantages, and along with that there are also certain disadvantages. They are low volume process, low in reinforcement content, and difficulty in removing all entrapped air. Quality may not be uniform with local unevenness. Longer curing times as room temperature curing agents are generally used. Labor intensive. Quality depends on skill of the operator, and it has a high waste factor. So next, let us see the compression molding method. Okay. So firstly we studied the contact molding. Now let us go to the compression molding method. So inside this, firstly, match die molding. So this is widely used method for long production runs from small to large sizes. Material to be shaped is pressed between heated matched dies with a pressure ranging from 50 to 100 megapascal depending on the flow characteristics of the feed material. The feed material flows into the contours of the mold at high temperature and then cures rapidly. Two forms of feed: sheet molding compound SMC and Duff molding compound DMC. So this is the steps for match die molding. Okay, so these are the match dies, and this is the material to be formed. So this is formed after forming, the mechanical pressure is applied, and this is the uh, this is the finished component. Okay, so this is basically the match die molding process. So here inside match die molding there are various types of compounds. Okay, so one is sheet molding compound SMC. So they are basically prepared sheet of resin fiber blend that contains all additives like curing agent, release agent, pigments, etc. All constituents are pre-mixed, so good consistency in finished product. Shelf life of around 3 to 6 months at room temperature. Then Duff molding compound DMC, blend of all necessary constituents with only short fibers. Resulting fibrous mixture has the consistency of a Duff. Shelf life less than that of a SMC at room temperature. Okay. So the forming methods employing gas pressure. So vacuum bag molding, autoclave molding, and pressure bag molding. So these are the forming methods employing gas pressure. So vacuum bag molding. So only one mold is used. A flexible membrane is placed over the mold, which is separated from the uncured laminate by a film of PVA, polythene or equivalent material, sealing of the edges and evacuating the air under the membrane. Thus, the laminate is subjected to a pressure of up to 1 bar. Curing to be done, which can be accelerated by placing the component in an oven or employing a heated mold. Okay, so that is vacuum bag molding. So this is the open mold forming method employing gas pressure, vacuum bag molding. Okay. So next is the autoclave molding. So it uses pressure in excess of atmospheric pressure like 5 to 15 bar. So mold is placed in an autoclave pressurized oven. Okay. So that autoclave is basically high temperature as well as high pressure. Okay. So it is placed in an autoclave with facilities for heating and pressurizing by a gas, usually nitrogen. So nitrogen is basically used in most of the most of the events, most of the tests or processes which involves gas pressure, because it does not react. Okay, it is a very inert gas. Okay, so in most, like, there are also tests, okay, like thermogravimetric analysis tests, so they also use nitrogen because it is non-reactive. So this autoclave molding, it is used for production of high density reproducible products for critical applications, like in aerospace industry. Okay, so this is an example of open mold forming method employing gas pressure autoclave molding. Okay, so then there is pressure bag molding. So it uses pressure in excess of atmospheric pressure. A flexible bag is placed over the layup on the mold. So this is the layup, this is the mold, okay, and this is the bag. Inflation of the bag by compressed air forces the layup into the mold. Okay, so that is how it is achieved. Like, the bag is inflated by the compressed air and it forces the layup, okay, into the mold. Okay, so open mold forming methods employing gas pressure, that is pressure bagging. Then there is closed mold system with low pressure. It consists of placing the reinforcement in a closed mold and then inserting the resin material into the mold to infiltrate the reinforcement. So it can use resin transfer molding (RTM), vacuum assisted resin injection molding (VARIM), reinforced reaction injection molding (RRIM). Okay, so these are the various techniques. So let us go through each of them also. So resin transfer molding (RTM). So it is a low viscosity resin. Here the low viscosity resin is injected into the closed mold using low pressure and normal temperature and then cured subsequently. It is inexpensive, facilitates the manufacturing of complex shapes and large sizes. It is slow. It has slow curing to restrict any temperature rise, and it has a slow manufacturing process. Next is the vacuum assisted resin injection molding (VARIM). So it has a low pressure. Here low pressure is obtained by extraction of air from the mold and then allowing atmospheric pressure or even lower pressure to force the resin into the closed mold. A reinforced reaction injection molding (RRIM). The resin and hardener components mixed at high pressures in an impingement mixing chamber and then injected into a closed mold where the pressure is usually less than 1 megapascal. So rapid curing and faster manufacturing processes present. Okay. So this is a schematic diagram of reinforced reaction injection molding (RRIM) as shown here. Okay. So now one more form of compressing molding method is the pultrusion. So let us study about that, about the pultrusion process. So it is an automated process for manufacturing composite materials into continuous constant cross-section profiles. In pultrusion, the product is pulled from the die rather than forced out by pressure. Different types of profiles such as rods, tubes, and various structural shapes can be produced using appropriate dies. Okay. So the reinforcement used consists of continuous fibers such as rovings or chopped strand mat or their combination, depending on the strength and rigidity required in the molded profile. The process consists of pulling continuous rovings and or continuous glass mats through a resin bath or impregnator and then into preforming fixtures where the section is partially shaped and excess resin and or air are removed. Then it goes into a heated die for continuous curing. Profiles have high strength and stiffness in the length direction with fiber content as high as 60 to 65% by volume. Okay, so main difference is here, instead of basically pressure, we basically pull. Okay, so that is the pultrusion process. Okay, so basic components of the pultrusion system are creels, resin bath or impregnator, heated dies, puller or driving mechanism, and cutoff saw. So this is the pultrusion scheme, okay, which is shown here. So here also the steps are also designated. So firstly, reinforcing fibers are mechanically pulled into a resin bath where fibers are saturated thoroughly and impregnated with polymer resin. Thereafter, saturated fibers are pulled through a machine precision die with entry portal and internal cavity in the shape of the final product. The composite is formed and cured within the heated steel die, and then upon exit from the die, the thermoset composite is cut to desired length. Okay, so that is the steps. These are the steps. Next, let us go understand filament winding. Okay, so this is applicable for fabrication of structures of revolution. Example: cylindrical and spherical shells, and your cylinders with hemispherical or toroidal and closures, economically and with high performance standards. Fabrication done with winding reinforcing fibers in the form of a continuous roving, which may be impregnated with resin just prior to winding, that is wet winding, or maybe pre-impregnated with partially cured resin, which is dry winding, onto a mandrel which defines the internal geometry of the structure. Okay, so this is a schematic diagram of filament winding process, as can be seen here. So the winding may be helical, where the mandrel rotates continuously and the fiber feed arm shuttles back and forth at speeds regulated to provide the required winding angles. Winding may be polar, where the fiber feed arm rotates in a longitudinal plane around the stationary mandrel. Mandrels should be able to withstand compression induced by the winding tension and also high curing temperatures. Steel tubes used as mandrel for tubular windings. Examples can be underwater pipelines, oil water storage tanks, air bottles, buoys, torpedo hulls, helicopter blades, etc. So it has multiple uses. So these are some of the examples of the FRP products. This in the form of FRP strips, FRP bars, FRP grids, and FRP pultruded sections. Okay, so these are the various products. In summary, we can say that in this lecture we basically understood the manufacturing of FRP products. So there we studied the three basic types: contact molding, compression molding, and filament winding. In contact molding we also studied about hand layup and spray up. In compression molding we studied about the match die molding, forming method employing gas pressure, closed mold method employing low pressure, and pultrusion. Okay, and filament winding also we studied. With this we come to the end of the lectures discussion. Okay, now let us also go through a few solved problems and understand how this the knowledge can be used. Okay, so let us enhance our understanding. So the first question is A1: which glass fiber has the lowest dielectric constant? A E glass, B S glass, C D glass, and D A glass or Da glass. So dielectric constant, if you remember, so it has a initial of D. Okay, so this D glass is the correct option. Okay, so if you can see here, D dielectric, it has a low dielectric constant. Okay, so C D glass is the correct option. Second question. Statement 1: properties of FRPC is strongly dependent on the direction of fiber. Okay. And statement 2: tensile modulus of glass fiber is generally more than aramid fiber. A. Only statement 1 is correct. B. 2 is correct. C. Both are correct. Or D. None of them is correct. So which is the right option? So if you remember, one of the property of FRPC is it is dependent on the direction. Okay, so direction of the fiber, that is along the axis. Okay, so along the axis it has the maximum. Okay, so therefore it is strongly dependent on the direction of fiber. So that is the correct option. So this only statement 2 is correct is so B and D are not correct. Okay, so only A and C, out of A and C, one is correct. Okay. And next is tensile modulus of glass fiber is generally more than aramid fiber. So this is the glass fiber, this is the aramid fiber, and this is the tensile modulus. So if you can see here, the modulus aramid fibers has a higher modulus than glass fibers. Okay, so aramid fibers has a higher modulus. Okay, or glass fibers has a lesser modulus. So it is generally lesser, not more. Okay, than aramid fiber. So it is lesser. That is statement 2 is wrong. Okay, so therefore only one is correct. Therefore A is the correct option. So as you can see, A, only statement 1 is the correct option. Third question: which of the following is correct regarding compression molding processing of FRP materials? Okay, A, hand layup, B, match die molding, C, spray up, or D, all of these. So if you remember, hand layup and spray up, okay, so these are examples of contact molding. Okay, so therefore only match die molding is the type of compression molding. Okay, So A, C and D all are wrong, only B is the correct option, match die molding. Okay, so as you can see here, match die molding is a type of compression molding, whereas hand layup and spray up are contact molding types. So B, match die molding is the correct option. Fourth question, which one of the following options is the property of thermosets? A, exhibit considerable strain at relatively lower stresses. B, cannot be recycled or reshaped by heating. C, chemically inert. Or D, all of the above. Okay, so which is the correct property of thermosets? Okay, so if you see here, basically, so this uh, exhibit considerable strain at relatively lower stresses. Okay, so these properties for thermoplastics. Okay, so exhibit considerable strain at relatively lower stresses. This property is thermoplastic. So therefore, this is not thermoset. So A is incorrect basically. Okay, then if you see here, chemical inertness and pleasing appearance. So chemical inertness is a property of, again, thermoplastic. Okay, so chemical inertness is not for thermoset, so that is also not correct. uh, so third is, yeah, so thermoset solidified by a chemical reaction cannot be recycled or reshaped by heating. Okay, so it is solidified by chemical reaction and it cannot be recycled and reshaped by heating, thermosets. So that is the correct option. Okay, so B, cannot be recycled or reshaped by heating, is the correct option. So B, as you can see, cannot be recycled or reshaped by heating is the correct option for thermoset property. Fifth question, statement 1, epoxy resin is superior to polyester resin in terms of mechanical properties. Statement 2, epoxy resin gives better adhesion to reinforcement fibers. A, 1 is correct, B, 2 is correct, C, both are correct, or D, none of them is correct. Okay, so if you see here, epoxy resin, they are superior to polyester resin in terms of mechanical properties. So in terms of mechanical properties, they are superior to polyester resin. So 1 is correct. Okay, and resistance to degradation by water and other solvents, and 3 gives better adhesion to reinforcing bars. So epoxy resin also gives better adhesion to reinforcing bars. So 3 is also correct. So both 1 and 2 are correct. That is C, both the statements are correct is the right option. As you can see, C, both the statements are correct is the right option. Sixth question, statement 1, pultrusion is a type of compression molding procedure for processing of FRP materials. Statement 2, in pultrusion, the product is pulled from the die rather than forced out by pressure. So A, 1 is correct, B, 2 is correct, C, both are correct, D, none of them is correct. Okay, so if you remember, pultrusion is obviously a type of compression molding. Okay, for processing of FRP material. So 1 is correct. And if you remember, it is the specialty is that the product is pulled, okay, rather than forced out by pressure from the die. Okay, so 2 is also correct. Okay, so both are correct basically. So as you can see here, it is an automated process. Okay, and it is a type of compression molding method, and product is pulled from the die rather than forced out by pressure. So both the statements are correct, therefore C is the right option. Seventh question, this is a numerical problem. The E-glass fibers in a polyester resin is 35% by weight. Given density of fiber rho f equal to 2.87 gram per ml and density of matrix rho m equal to 1.08 gram per ml, what is the ratio of volume fraction of matrix and volume fraction of fiber? A, 2.78, B, 3.59, C, 4.94, or D, 5.86. Which is the correct option? So we need to find out the ratio of volume fraction of matrix and volume fraction of fiber. Okay, so if you see here, this value Wf equal to 0.35 is given in the question. So Wm is equal to 1 minus 0.35 equal to 0.65. So we are considering the composite to be void free. Okay, so rho f equal to 2.87 gram per ml and rho m equal to 1.08 gram per ml. So using this relation, we can find the rho c value, which is 1.3816 gram per ml. Okay, so using this, we can find, so if you remember this equation, so Wf equal to rho f by rho c into Vf. So from this we can find the Vf, which is basically the volume fraction of fiber in the composite, which is equal to rho C by rho F into WF, which is equal to 0.1685. And VM is simply volume material matrix volume fraction. It is 1 minus VF because void free. So that is 1 minus 0.1685, which is 0.8315. Therefore, ratio of matrix by matrix volume by your this fiber volume, that is nothing but 0.8315 by 0.1685, 0.8315 by 0.1685. So that is equal to 4.9352, which is equal to 4.94. Okay, so C 4.94 is the correct option. Eighth question: the weight of the matrix in a void-free glass or epoxy composite is measured to be 40% of the weight of the composite. The specific gravities of the epoxy and glass are 1.5 and 3 respectively. If the elastic modulus values of fiber and epoxy are 75 gigapascal and 3.5 gigapascal respectively, find out the density of the composite in gram per ml. So the answer, what is the answer? Is it A 2.14, B 3.78, C 1.57, or D 4.86? So if you remember this relation, VF equal to WF into rho C by rho F, and VM equal to WM into rho C by rho M. Okay, so VF by VM from these equations, it will be equal to 0.75, and that is equal to so that is found by these values. Okay, substituting the values, so it is 1 minus 0.4 by 3 into 1 divided by 0.4 by 1.5 into 1. Okay, and the density of water we all know is 1 gram per ml. So here glass is the fiber, epoxy is the matrix. So VF plus VM equal to 1. Solving, we get VF equal to, so using these two relations, we get VF equal to 0.43 and VM equal to 0.57. Now VF plus VM equal to WF into rho C by rho F. So substituting these equations, plus WM into rho C by rho M, which is equal to 1. So therefore rho C equal to 2.14 gram per ml, right? So this is basically the density of the composite, 2.14 gram per ml. So therefore it is A. Okay, A 2.14 gram per ml is the right option. Ninth question: the weight of the matrix in a void-free glass or epoxy composite is measured to be 35% of the weight of the composite. The specific gravities of the epoxy and glass are 1.85 and 4 respectively. If the elastic modulus values of fiber and epoxy are 80 gigapascal and 3 gigapascal respectively, find out the ratio of load shared by fiber and epoxy. A 8.5, B 16, C 10, D 23. So what is the ratio of load shared by fiber and epoxy? So let us check this. So VF by VM is equal to 0.8589 as calculated using these equations. And since it is void free, VF plus VM equal to 1. So substituting, we get VF equal to 0.46 and VM equal to 0.54. Now VF plus VM equal to 1. So using these equations and the relation, we get rho C equal to 2.84. Given EM equal to 3 gigapascal and EF equal to 80 gigapascal, therefore for the composite, epsilon C equal to epsilon F equal to epsilon M, and sigma F equal to EF epsilon F, and sigma M equal to EM epsilon M. So sigma F by EF equal to epsilon F equal to epsilon M equal to sigma M by EM, or sigma F by sigma M equal to EF by EM, which is equal to 80 by 3. Implies sigma F equal to 80 by 3 sigma M. Now VF equal to fiber volume fraction equal to VF by VC, which is equal to AFL by AFL plus AML, which is equal to AF by AF plus AM equal to 0.46. And here, because length will be constant, so it is cancelled. Okay, and therefore AF into 1 minus 0.46 is equal to 0.46 AM. Therefore AF equal to 23 by 27 AM. Now PC equal to PF plus PM. Okay, so that is the total strength, total load. Okay, and therefore basically using these relations, okay, uh, we get the PF. So basically using these relations, we get PM by PC value equal to 0.04. Okay, because PC equal to 23.716 PM. Okay, and therefore PF by PC equal to 1 minus 0.04, that is 0.96. Hence the ratio equal to ratio of load carried by fiber and epoxy, that is matrix, will be PF by PM, which is equal to PF by PC by PM by PC, which is equal to 0.96 divided by 0.04, that is equal to 24, which is nearly 23, because 24 is not the option provided, so we will take the nearest option, which is 23. So D, 23 is the right option. And last question, 10th question. A glass epoxy specimen weighing 1 gram was burnt and the weight of the remaining fibers was found to be 0.5 gram. The densities of glass and epoxy are 3.2 and 1.75 respectively. If the actual density of the composite was measured to be 2.05, what is the void fraction in percentage? Is it A 6.5, B 7.2, C 8.6, or D 9.4? What is the void fraction? So here we are basically considering the void fraction. Okay. Weight fraction is Wf equal to 0.5 and Wm is equal to 0.5. So for matrix it is 0.5, and for fiber also weight fraction is 0.5. Rho c is equal to 2.05, which is given in the question. Rho f equal to 3.2 and rho m equal to 1.75. So therefore Vf plus Vm plus Vv equal to 1, or Wf into rho c by rho f plus Wm into rho c by rho m plus Vv equal to 1, or 0.5 into 2.05 by 3.2 plus 0.5 into 2.05 by 1.75 plus Vv equal to 1. So therefore void fraction is basically 0.094, which comes out to be 9.4%. Okay, so that is D. Okay, so D, 9.4% is the correct option. With this, we will end today's discussion on the fourth lecture. So let us meet next Sunday to go through the lecture and discuss the fifth lecture notes, along with the basically the also go through the lecture, as well as go through the solve problems and understand the various ways of retrofitting using the fiber reinforced polymer composite structures. Okay. So with this, I would like to end today's discussion. Have a good night. Thank you.